The Story of the Atom by Brianna and Erica.
A long, long time ago, actually, it was about 2,500 years ago, which was before Socrates or Plato or Aristotle or any of the Greeks you may have heard about, there lived a man named Thales. He's said to be the world's first philosopher-scientist, the first to look for explanations and observe facts, not myths. He was the first scientist to leave his name on his ideas.
Thales tried to discover a basic unit or element of life. Water, which takes three forms. Solid, liquid, and gas, seemed logical. It was a reasonable start for a search that continues today. The world is full of differences, and yet Thales had the idea that underneath all the complexity there is a plan, some call it divine plan, that explains everything. Thales asked, what is the nature of matter? By that he meant, what are we made of? What is the world made of? Is there one thing that ties everything together? Thales said life's basic unit is water. Another Ionian, Anaximenes, said it was air. Other Greeks said fire or earth. Fire or earth. Empedocles, who lived in the 5th century, said it was all four of those: earth, air, fire, and water. That idea of four elements, earth, air, fire, and water, was one of the longest lasting and most influential scientific hypotheses in all of world history.
Empedocles was wrong in the elements that he chose, but right in the idea that instead of a world where everything is different and unrelated, there are certain basic substances that combine to make up everything else. We now realize that earth, air, fire, and water aren't basic elements. It was the Ionians who got us searching in the right direction. Pythagoras was born in 582 BC on a Greek island, Samos, which has a world-class prosperous port. He tied philosophy to mathematics. How do you make sense of the universe? Is it a messy place that takes on meaning as we slog through mountains of information, trying this, trying that, adding one block of knowledge to another? Or is it an orderly, perfect creation that can be understood through mathematical formulas and headwork?
For Pythagoras, the way to understand the universe was by searching for things that are absolutely true, and numbers seemed perfect for that. He believed numbers were divine, an expression of God's mind. He found that the sounds of exact number relationships that gave order to music that no one had imagined before. Okay. The square of the hypotenuse of a right triangle equals the sum of squares of the other two sides. It is called the Pythagorean theorem.
Democritus was born in Thrace, which was an unfashionable, out-of-the-way place for a philosopher. Democritus believed that to understand the universe, you need to know what is it made of. Democritus thought there must be something still smaller, something that unified these elements, something they all had in common. He said there had to be a smallest substance in the universe that can't be cut up or destroyed and is basic to everything else. He called the smallest substance an atom, from atoms, which means unable to cut. The atoms that Democritus had in mind were solid, hard, and compact. Nothing could penetrate them. They were in the constant motion, and they were small to be seen.
Socrates, who lived in Athens, was called for the wisest man in the world by the oracle at Delphi, turned from physical science to a study of human soul. Experiments were proving that Empedocles' four substances, earth, air, fire, and water, were not the uncuttable elements he thought. Robert Boyle, the Irishman who came up with the famous gas law, said that gases must be made of tiny corpuscles with a lot of empty space between them. Newton talked about impenetrable particles. Finally, an English Quaker named John Dalton came along, and his timing was right. He understood that there are basic substances known in science as elements that cannot be broken down into simpler components by chemical means. Dalton thought it might might have something to do with atoms. He did his own experimenting and measured with scientific precision, but he went still further. An inquiry into the relative rights of the ultimate particles of bodies is a subject, as far as I know, entirely new. But there was no way to measure the mass of an individual atom. What could he do? Because of the study of gases, Dalton knew that elements always combine in fixed amounts, the same ratio weight to one another. It's called the law of definite proportions. That gave him a breakthrough thought. Imagine a crate with an equal number of red cups and green saucers. It falls off a forklift. Crash. A heap of green shards and red. You need to know the relative weight of a cup and a saucer, but you don't have either. What do? You weigh each pile and compare their weights. The ratio between the pile of red and pile of green is the ratio of the weight of one cup to one saucer. Dalton knew that if he weighed equal amounts of elements, he could assume equal numbers of atoms and get the ratio of their weights. Dalton said each element has unique atoms. It is the weight of its atoms that identifies the element. He said that every atom in an element is alike and has the same weight, and atoms of different elements have different weights. He prepared a table of atomic weights. He was way off on some of them, but it was the start. Dalton went on to say that atoms can neither be created nor destroyed, and that chemical reactions are rearrangements of atoms. He understood that atoms that are unlike can bond in a firm union to form substances that are not elements. They are called chemical compounds. But he didn't know about molecules, which are groups of two or more bonded together, and he didn't know about isotopes, which are slightly different from their sisters. Most important, he had no idea that atoms have innards, and that number of protons inside each atom determine its characteristics. Dalton talked of atomic weight. Today we talk of atomic number, meaning the number of protons.
Atoms turned out not to be as solid and impenetrable as Democritus and Newton thought. They were not like hard billiard balls, as Dalton described them. In the 20th century, a nucleus and still smaller particles would be found inside the atoms. At the end of the 19th century, a scientist called J.J. Thomson discovered the electron. This is a tiny negatively charged particle that is much smaller than any atom. An atom is the smallest particle of an element that can still be defined as that element. Electrons are tiny, negatively charged particles that orbit the nucleus of an atom in energy levels, or shells. But where had these tiny particles come from? Since they were so small, Thomson suggested that they could only have come from the inside atoms. So Dalton's idea of indestructible atom had to be revised. Thomson proposed a different model for the atom. He said that the tiny negatively charged electrons must be embedded in a cloud of positive charge. No overall charge, so that charges must balance out. Thomson imagined the electrons as bits of plum in a plum pudding, but with lots more space in between.
In 1911, Ernest Rutherford interpreted these results and suggested a new model for the atom. The positive charge must be concentrated in a tiny volume at the center of the atom. Otherwise, the heavy alpha particles fired at the foil could never be repelled back towards their source. On this model, the electrons orbited around the dense nucleus, center of the atom. The next important development came in 1914 when Danish physicist Niels Bohr revised the model again. It had been known for some time that the light given out when the atoms were heated always had specific amounts of energy, but no one had been able to explain this. Bohr suggested that the electrons must be orbiting the nucleus in fixed energy levels, or shells. The energy must be given out when excited electrons fall from a high energy level to a low one. In this model, electrons can only be one of those fixed energy levels, but alas, his model didn't work for any atom that had more than one electron.
Austrian physicist Aaron 1887 through 1961 devised a mathematical equation to describe the behavior of an electron, which was different than a large moving object like the other models. The solutions to this equation became the quantum. This model gives the likelihood for finding the electron in a given three-dimensional space called an orbital. This description is similar to a rotating propeller blade. The propeller blade has the same probability of being anywhere in the sphere at any given instant, but you cannot tell.
Okay, and this is what an atom looks like. That is the nucleus right there. And that is the story of the atom.
Bye.
Bye.
We love you.